Hey guys, welcome to chapter 9. We did video 1 kind of in class as a lecture, so I'm jumping in with video 2. But I'm actually going to finish up the tail end of the first lecture's notes because we didn't quite get to some of it. It was a little bit rushed, so I want to make sure that everybody's good there. So I'm just going to do that and then I'll move into the next stuff. Okay. So we were talking about sequences and series, and we were talking at the end of class specifically about in a geometric sequence, if it's infinite, which this is because of the dot, 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 can we sometimes add together a series or a sequence and get a sum that is finite? So yes, we can. So that is something we're going to talk about here. And we talked about it, alluded to it a little in class. First, let's find an expression for the nth term. Okay, our rule for a geometric sequence is start with your value, your a sub 1. What are we multiplying by? Looks like I'm multiplying here by 2/3 to the n minus 1. Now, because these are the same thing, you could actually make this 2/3 to just the n. And again, the reason that that works is because your multiplier is 2/3. So this is kind of like 2/3 to the first power, and then you're adding the exponents together. You do not have to. This is totally fine. Do I think that I could find a sum of the infinite number of terms? And then why? Again, some of us, I can't remember if each class did, but we talked about this in class. If what you're adding is getting smaller and smaller, so in this case, 2/3 and then 4/9 is smaller, 8/27 is smaller. What you're adding is you're basically adding something that's getting closer and closer to 0. And so as you begin to get so small, like think about this. I mean, eventually, if I look at the actual decimal values of these things, these numbers start to get so small that you're adding like 0.0000000 something. So you're basically adding nothing. So yes, we do get this finite sum. So then what case would that happen in? Well, we said the numbers have to keep getting smaller. And so your R value has to be between 0 and 1. That would make your numbers smaller every time. So as long as the number you're multiplying by is less than 1. So like in this, for example, in this one, my R value is 2/3. So I could do this. So let's try to find a formula for it. So in class, we found a formula for the geometric sum that was finite by kind of comparing these two sums together. So here's the original geometric sum. Here's it written out. First term, then times r, times r, times r, times r, and so on and so forth forever. Okay. I want you to look at what I did next. I factored out an r from every term from here forward. So see that? I factored an r out from every term going forward. So what happens? That means that each one of these basically goes down by a power. Everybody see that? And not only that, but what's left inside is this whole original first sequence, or G. So that means that the sum is really equal to a plus r times itself, times the whole geometric series. So then we can solve this pretty easily. We can bring the G terms to one side because that's what we're trying to solve for. We can factor out the G to get it alone, and we can divide. So this is your formula for the infinite geometric sum. But again, this only works if r is between 0 and 1. We could also get that from the finite one. If you think about it, if I look at the finite sum, if my r value is something between 0 and 1, so maybe, for example, 2/3, if I have an infinite number of terms, meaning your n value is getting bigger and bigger, like your n value is going to like, millions, because, right, we're going to infinity. What's going to happen if you plug in like a million here? If you have 2/3 to the 1/millionth power, remember it's getting smaller and smaller. This position is getting closer and closer to what number? Again, like 2/3 to the 1/million. 0. So basically that part would become a 0. 1 minus 0 is 1. Check out what happens. It would just become this. So there's kind of, that way isn't really a true proof, but it is looking at logically how you could create that. Okay. So let's try to find the infinite sum for the one that we just did. So let's do, what did we have? I think we had 2/3, 4/9, right? 8/27, and so on and so forth. So if we wanted the infinite sum, which I would tend to write like this rather than G. So the infinite sum would be your first term, 2/3 over 1 minus your ratio. Your common ratio here is 2/3. So you get 2/3 over 1/3. You can multiply by the reciprocal and you get 2, which is basically, if you kept going forever and ever, the sum of this series ends up being 2. Okay. So then, before I move on to the next one, let me just show you a couple applications of this type of a situation, like both arithmetic and geometric. So I'll do an arithmetic one first. Okay. So, for example, I could say, I think I was starting to do this one in class and then got cut off. Like if you had an auditorium, right, and you had seating, and that seating increased maybe by the same amount in each row. So what I mean by that is maybe there's like 10 seats in the first row, maybe there's 14 seats in the second row, 18 seats in the third row. You get the idea here. And then maybe you could say maybe there are 15 rows. Okay, so one application for this could be you want to find out how many total seats there are, right? Okay. In the auditorium. That would mean you need to add together all the rows. And you need to go from, let's think about this, we would have 15 terms because we'd have a sub 1 all the way through 15 rows. Okay, so if you want the sum of 15 rows, let's think about this. For arithmetic, probably wouldn't hurt to remind yourself what the formula is. It's the number of terms divided by 2 times the first plus the last. Okay, so number of terms is 15 over 2. The first term is easy, 10. Now the last term we don't have, so that would probably be helpful if we wrote the rule for our sequence. So the rule is we started with 10, we add our common difference, which is plus 4 times n minus 1. If you want to simplify this, go for it. So we need the 15th term. So I've got, oops, that's supposed to be a 14. So then my 15th term ends up being 66. I needed this rule so that I could get this term so that I could plug it in over here because I needed the last term or the 15th term. Okay, so then I end up with 76 times 15 over 2, and I get, let's see, 570 seats. And then, of course, if I wanted to make the question a little bit harder, I could say, like, okay, if I sold each seat for blank amount, how much would I make? There you go. Okay. I could also say, I could up this a little bit more. Let's see. I'm going to change it slightly. So I could also tell you what I want the sum to be, and you could solve backwards. So what I mean by that is I could say something like, okay, what if you know that there are 1,050 seats? How many rows, right? Like you could go back and figure this out. So again, this would be the sum. So I would start with this. Well, I know that the sum is going to be 1,050. I don't know how many terms there are, but I am going to, once I know that, I'll divide it by 2. And then I do know my first term. My first term is still 10. The question is, I don't know this last term. And unfortunately, I don't know how many rows, so I can't solve, like I can't get an actual physical, integer number. So what I can do is use the rule though. Check this out, guys. I need to plug in a sub n because I need the last term, right? So let's look at what a sub 10 would be, or a sub n would be again. So my last term would be whatever 10 times 4, oops, it's just your rule. So here we go. Because remember, this is a sub 1 plus a sub n. Well, we don't know n, but we know that the last term will be whatever the heck we get when we do 10 plus this. I'm going to simplify it, so that becomes plus 6. So then I'm going to replace the a sub n, the last term, with 4n plus 6. Now I can solve. Okay, I'm actually going to multiply by 2 first, so I get 2,100. I'm going to distribute the n. So I get 10n plus 4n squared plus 6n. I'm going to bring everybody to one side and then solve this guy. Now, I could solve this either by factoring or I could solve it by quadratic formula. I can see that I can divide everybody by 4, so I'm going to start with that. Maybe the factoring will be a little easier. So then I get 2100 divided by 4 is 525. It's not that much better. If you don't want to do factoring, you can always go to quadratic. Negative b plus or minus b squared minus 4 times a times c all over 2a. So let's see. This ends up being 16 plus 4 times 525. And the square root of that comes out beautifully, which meant it was factorable. So the square root of this number under here becomes 46. So then that means my two choices are negative 4 plus 46 over 2. So I get 21 is one of my choices. Or negative 4 minus 46 and then divided by 2. So that would just be negative 50 divided by negative 25. Now think about this, guys. These are n values. You guys should know that n describes the term, and we have to start with like n equals 1, the first term. So I can't be negative. So the only thing that could work here would be 21. So you would know this would be 21 rows. That one is a little tricky. You might want to watch that a couple times. Okay. And then for a geometric one, let's just look at one real quick. Let's do, I'm not going to do an infinite one. I'll do a finite one. We can do more infinite ones in class. For an infinite one, or I'm sorry, a finite one, you could be this. Like, let's say we're talking about your salary. And you got a great job out of college and you make $60,000 your first year. Not too shabby. And then they said, well, we're going to give you a raise yearly, which isn't always necessarily true, but let's say they did. They said, we're going to give you a raise of 1.5% or 0.015. So that means that you are going to add that to your salary every year. Now, you could multiply this number by this, but you'll only get your raise amount. So my suggestion would be to multiply that instead by 1 plus this, right? Because then that'll give you 100% of your salary plus the extra. So let's see what we get. 60,000 times 1.015 gives me 60,900. Okay, this is going to be a little hard to tell because of, I'm going to use a dollar sign. 60,900. Okay. And then I'll multiply by the 1.05 again. Oh, 1.015, excuse me. So I get about $61,813.50, you know, and then that's going to keep going as I go on. Okay, so let's say that the question said, let's find your total amount made, so your total money over the first 5 years. Not how much do you make during your 5th year. That would just be plugging in. We can do that too. Well, let's do that too. How much do you make during your 5th year? We'll do that first, and then we'll do how much do you make over the total 5 years. Okay. So if I want to know how much I make during my 5th year, then that means I want the specific term. So I need the rule. So my rule is initial value. What are you doing to the initial value? You're multiplying it by 1.05 to the n minus 1. If I want during the 5th year, then this is obviously just going to be to the 4th. So I can plug that guy in. I could round to the nearest penny, and I get about $62,740.70. So that's about how much you'd make during your 5th year. If I want to find the total you made, then this you should recognize as being the sum. So I want the sum over the first 5 years. Remember the formula for the finite sum, because we're only going to 5 years, is first term, 1 minus r to the n over 1 minus r. So let's do it. First term, 60,000. 1 minus, what's your r value? Careful, it's not just this, it's that. Your multiplier is 1.015. We're going to go to the 5th power, all over 1 minus 1.015. Okay. So if I was doing this in the calculator, I do have to be careful about how I plug this in. So I've got my calculator out here and I'll show you just so you can get a feel for that. So when I plug this in, I like to do, you can do the fraction bar, you can do what's in the parentheses first. I usually do the 1.015 if it's a nasty number, which this isn't the nicest of numbers. So I would do this guy to the fifth. I'm going to do that first. Cool. Then I'm going to do 1 minus that, which is what's in the parentheses, the 1 minus answer. That's this. Then times 60,000. Cool. And then I need to divide by this. Now, I could do this in my head, or I can do divide, but I'm going to have to put this in a parentheses, which is fine. Okay. All right. And so our sum ends up being, here we go, $309,136.02-ish. So 309,136. Oops. 309,136 and 2 cents. So this is how much you made over your first 5 years. Seems like a lot, but wait till they take out taxes and you got to pay for your rent and all that other good stuff. But still, kudos to you for getting a good job right out of college. Okay, so now you got a chance to see kind of how those sequences and series work. And we will do a little bit more with them. I'll do some in class where I give you like a couple of terms in the sequence. Like maybe I give you the second term is 2, and maybe I give you another term in the sequence is like 15, and I'll tell you, oh, it's arithmetic, and you have to figure out what's the rule. Or, oh, it's geometric, what's the rule, right? That's kind of where we're headed next. Okay. Okay, so switching gears. Let's pop over to the second part of the video, which is counting rules. So this is the second part of this, the second video in this sequence. So what we're trying to figure out is basically how many of each, like how many ways can I do certain things? So for example, like if I wanted to, I think I said this in class, if I wanted to put together like an outfit, and that outfit contained picking a shirt or a top, picking some kind of a pant or a bottom, and maybe picking some kind of a shoe. Depending on how many of each choice you have, like maybe you have 5 shirts, you have 7 pairs of pants, and 3 pairs of shoes. We want to know how many different ways can we do this. That's what these counting rules are. That's what we're talking about. So sometimes some of the things that we need to consider, and we'll talk about this as we get into it, is how many different sets are you choosing from? So like how many different moments within your choices do you have? So how many different sets? Are you allowed to repeat? Like could you wear 2 pairs of pants of the same pant, which you can't here? Does the order of the elements matter? And then some other things will come up. Some of them are easy and some of these situations get more difficult. Okay, so let's start with this. So we have this idea of independent choices. So independent choices are just the pools of items that you can choose from, right? So these could be, so these are the different things, like a shirt was an independent choice, pants was an independent choice. So basically, how many different items are you choosing from? Those are called independent choices. So I kind of did the same one that I was talking about here. How many outfits can a person make if he or she has 6 shirts, 2 jackets, and 5 pairs? If you have just independent choices, you literally take the number you have in each independent choice and you multiply them together. So like for shirts, I have 6 choices, times jackets, I have 2 choices, times slacks, I have 5 choices. And so I end up with 60 different totals. They're considered independent because what I choose for a shirt doesn't affect then what I choose for the jacket or slacks. That's independent choices. Okay. Selections. Selections is when you have just one pool of items and then you select repetitively from that. So like, let's see, I'll try to do an easy one. Like if I had a bag or a bowl and I filled that bowl with marbles or something like that, and I was choosing items out of this and I kept choosing from this, right? Okay. That is a selection. Now, sometimes you can select something and then replace it in the pool, which means you always have stuff to choose from. So like I would take out a marble, see what it is, and put it back in. sometimes we can't replace, and so then you can't repeat items, which means you eventually would exhaust your pool. Okay, so those are our selections. Okay, if you are able to repeat, if you can put things back into the pool and they're unique, that's the other thing. So like if each of these marbles was a different color, let's think about that. Well, if I had, I think I've got 7 here. So if I have 7 different colored marbles, how many choices do I have for the first marble I pull? 7, because you have 7 different colors. They're unique. Then if you put it back in, you'd have for your second, if you pulled a second marble, you'd have 7 choices again, and so on and so forth, as many as you needed to do. So we say that you have n unique items, which in this case 7, and you're going to take it to the r, which would be how many you choose. So like if I wanted to choose 3, if I'm picking 3 marbles and I replace it each time, then that would be 7 to the third. I'd have 7 to the third possible outcomes. Okay? Okay. So let's do a couple of examples. How many different sets of outcomes can we get when we flip a fair coin 20 times? Well, think about it. Each little independent selection has how many choices? Well, if you flip a coin, you can either be heads or tails. So you have 2. And then you're going to flip it again, and then you're going to flip it again, and you're going to do this 20 times. So you'd have 2 to the 20. How many 3-digit numbers can be formed using the digits 1 through 9? Inclusive means you can be 1 and you can be 9, but you can't have zeros, so no zeros. Well, let's think about it. We're going to choose 3 digits. So we have 3 independent choices. You have 9 digits to choose from. 1 through 9 is actually 9 digits. So the first one you have 9 digits. Because you can repeat, you still have 9 digits to choose from here and 9 digits to choose from here, which is why you end up with 9 to the third, or 729. We're going to talk about what happens if you can't repeat in a second. That's a selection. Okay, permutations. Permutations is like a selection. There's still one pool of items that you can choose from without replacement. So you don't put them back in, meaning you can't get them more than once. That's what a permutation is. So the order matters here of how you pick the elements. And we'll talk about that more as we go on. So in general, I'm going to go right down to the example. In general, this would be like saying how many 3-digit numbers can be made if you only use each number once. So you're not going to use a number more than once. Well, you could think of it as an independent choice. You have 3 independent choices, the 3 digits. 1 through 9 are 9 possible choices, but then you don't replace the number you use. So now you only have 8 to choose from digits, and then you only have 7 to choose from. And so we get 9 times 8 times 7, or 504. Okay. There's also a formula for this. It's, again, this is called a permutation. And so we write this, there's a couple of ways to write this. We write this as a permutation. We use a capital P, and we say n comma r. Now this n and r are the same as the n and r I talked about before. N is the number of objects in the pool, and r is how many you choose. Okay? And the way that we get that, and your calculator sometimes does NPR, not like the radio station, but that's how they write it. So they'll put the total number of objects, how many you're choosing. And the quick way to do that is n factorial, which is the way you could choose all the objects, over n minus r factorial. This is another way to do it. Now let's see that in action for this problem. So if I was doing it in this problem, which I would probably just do it like this, but you can use the formula, that would be 9 objects permutated 3 at a time, because I'm going to take 3 of them. So that would be 9 factorial over 9 minus 3 factorial. Factorial just means, I hope everybody knows this, 9 times 8 times 7, you go all the way down to 1. So I get 9 factorial on top over 6 factorial. Now think about this. If I start to expand 9 factorial, I start going down. Why would I stop at 6 factorial? What would happen at that point on top and bottom? Yeah, those would cancel. So I do just get 9 times 8 times 7 because they cancel out. 2 different ways to get a permutation. We're going to get to use this plenty in class, so you'll get plenty of practice. All right, and then the last one that we're going to study is called a combination. So a combination, still one pool. However, the order in which they are chosen is irrelevant. So that means that This is like if you have a group or a committee. Like if think about it like this, guys. If I looked at our whole class and I said, I'm going to choose 3 students to be on a committee to help me, I don't know, prepare for a class party. So let's say we were in person. Then it doesn't matter the order. Order doesn't matter because it doesn't matter that I picked so and so first or so and so second. It just matters that they made it on the committee, right? If I were to say, well, the first person I choose is allowed to pick, the snacks, the second person is allowed to pick the movie we watch or whatever, well, then order would matter because then those things would have roles. So again, you want to think of combinations as when you're having like groups or committees or things where, again, the order doesn't matter. Okay, so how do I do combinations? So combinations are like permutations, but we have to take out the repetitive items because order doesn't matter. So again, I'll talk more about this in class, but the basic idea here is this. So take a look at that. So a combination of n objects taken r at a time it starts off like a permutation, n factorial over n minus r factorial. Look at the extra little piece. You're going to divide out by r factorial. That actually gets rid of the repetitive ones, the ones that that I would choose if order did matter. So again, let me show you what I mean. Let's say that we had the letters A through Z, and I was going to pick 3 letters. If order matters, then me choosing A, B, C is different than A, C, B. Do you guys see what I mean? So if this is a permutation, I count these. I'm actually going to do one more. I'll also do CAB. So if this was a permutation, each of these is a choice. Each of these is a different version. If this is a combination, the fact that I chose A, B, and C is only one choice. So this is not considered a new version, and this is not considered a new version. So combinations are a much smaller set of data than permutations because you lose all the other versions where they're mix and matched. So again, we'll talk about that. So by dividing by this r factorial, you basically get rid of your repetitive ones, the ones that are the same but in a different order. So let's see what it looks like as a problem. How many groups of 6 objects can you make choosing from a set of 9? And when I say distinct, that means that they're not repetitive, so they're different items. Okay, because I'm saying groups, order does not matter here. You know it's a combination. You know you're doing 9 total different objects. You're taking them 6 at a time. So I get 9 factorial over. Technically, it was 9 minus 6, which is 3 factorial, but don't forget you have this extra r factorial on the bottom. So I have a couple different ways of doing this. On top, I immediately stopped at the 3 factorial and canceled. You can see here I canceled the 3 factorial. And then I still have this on top and I have the 6 factorial left. But then I can still cancel some of these things. So I could do some of this by hand. And then I have 9 times 8 times 7 over 3 times 2 times 1, or 84. So there's 84 different ways that I could do that. Okay. Okay, so we're not doing expected value. Okay, so let's try some of these. You can pause this if you want and try. We're going to see which ones are selections, which ones are combinations, and which ones are permutations. So if you want, you can hit pause and you can try putting these where you think they go, and then you can start it up again. Okay, so let's start with card hands. So with mathematicians love to use cards as examples for these. So in card hands, think about this, guys. Let's say it's a poker game. So you're going to be dealt 5 cards. Does the order that you're dealt the cards matter, or does it just matter that you get that card in general? It just matters that you get that card in general. So if you're talking about your hand, order does not matter, which immediately makes this a combination. So if you're doing anything with cards, it's a combination. Rolling dice. If you're rolling dice, let's think about this. Rolling dice, each roll is a independent choice, and we have the same amount. We're never going to exhaust our set. So we can call that a selection. Okay. Officers for a club. If you're choosing officers for a club, officers would mean that like you have maybe like a president, a vice president, a secretary. That means that who I choose for president is different from who I choose for vice president. So order matters. So whenever there are roles, that's always a permutation. Okay. Ordering a car. So if you're ordering a car and you're choosing a bunch of different options, remember, it doesn't necessarily matter the order you choose the options. Like if I choose that I want it to be red on the outside but gray on the inside, that is, order doesn't matter on that situation. It just matters that you choose the gray outside and the red inside. So that would be a combination. Taking friends to a movie. So if you're taking friends to a movie, in theory, it doesn't matter the order you pick them. It just matters which friends you choose. So this should be a combination. Now, for some of you, who you call first might matter. So maybe you would say permutation, but technically it's a combination. Flipping coins. Flipping coins, again, it could technically be considered an independent choice. It could also could rolling die. Again, independent choices are, you just have, each of its own pool. So I would say in this case, it could be technically considered an independent choice or a rolling dice, but you could kind of go back and forth on that. Race with medals awarded to top finishers. The first thing I would notice is they talk about finishing, which means there's places or roles. Boom, permutations. A fixed price meal, choosing your appetizer, entree, or dessert. So here's where you have these independent choices. Choosing your appetizer is independent of what you choose from your entree, is independent of your dessert. You're going to multiply all those together. That's definitely independent choice. Again, flipping coins could kind of be here, but it could also kind of be under selection. So again, this is definitely an independent choice problem. And then committees, anything with committees, guys, immediately should be under combinations because committees order doesn't matter. There's no specific role. You're just a part of a group. These are going to be important because then you can figure out how to attack a problem. So make sure that you're comfortable with doing that. Okay, so let's just do a couple problems and make sure everybody feels okay with that. Let's try okay, let's make some license plates. So we're going to make some license plates and we're going to say that they can be alphanumeric. We'll talk about that in a minute. And let's say that there are seven of those, 7 characters. And let's do that we can repeat. And then let's try it with no repeats. You guys can think about which number you think is going to be bigger. Do you think it's going to be, we're going to have more choices if we are allowed to repeat or more choices if we can't repeat? Okay, alphanumeric would mean I can be any of my alphabet characters, which are 26. And then numeric are 10, typically 0 through 9, which is actually 10 choices, by the way. So then that would be a total of 36 characters that I can choose from. So I have, my license plate is going to have 7 spaces. So you can think of this in a couple of different ways. You can think of this, you could think of it as an independent choice, where each one of these is an independent choice, right? You could also, we'll talk about how you can also think of it in a second. Okay. So if we can repeat them, let's think about it. How many choices do you have for characters in your first slot? Alpha or numeric? 36. If we're allowed to repeat, how many choices do we have for our second slot? 36, 36, so on and so forth, which is 36 to the 7th. So that's like a selection. It's a very large number, and I'm not going to write it down, but it is a very large number. What if we can't repeat? Well, if we can't repeat, again, you can think of this as an independent choice where I have 36 choices for the first character, but then it goes down to 35, to 34, to 30, to 33, to 32, and so on and so forth. Let's see, 1, 2, 3, 4, 5, 6, 7. So 31 and 30. If you're not allowed to repeat, you can also think of this as a permutation because order matters. So I could also think of this as 36 permutated 7 objects at a time, or 36 factorial over 36 minus 7, which remember gives us 29 factorial, which means this would stop at 29 because those would cancel. So same thing. Now you can do this in your calculator, so let me show you where those are real quick. Permutations and combinations in your calculator are under, if you go to math, you're going to go over to this probability column. There they are. Permutation, combination. So this is a permutation. I have to put so some calculators will actually put this in the subscript, like you can put the numbers here. If it doesn't, you have to put the first number you want first and then the second number you want after. So I want to do 36. I'm going to type in 36 and then I'm going to do NPR and then I'm going to say 7. Do you see what I'm saying? And so this is going to read this as 36 permutated 7. Some of you, again, it'll let you put the 36 here and the 7 here. Woo, that's a big number. And then this is technically compared to the 36 to the 7th, which is the one where we were allowed to repeat. So which one ended up being bigger? Obviously, the one where you were allowed to repeat values because you had more choices in each spot. Okay, so there you go. So that's one way of doing this. Now, these can get really complicated because I can say something like, maybe it's the same thing, same idea. We have a license plate, but maybe you have 7 total characters and maybe the first 3 are numbers and maybe the last 4 are alpha characters. And you are allowed to repeat, right? Okay, I would do this as independent choices, at least to start off with. And then we can look at it another way. The first 3 are numbers, so that's 0 through 9. So we have 10 choices. We're allowed to repeat, so the first 3 slots would be 10 times 10 times 10. And then the last 4 are alpha, which there's 26 characters. Again, if we're allowed to repeat, we could do that. Okay, what if no repeat? If no repeat, then it would go 10, 9, 8, 26, 25, 24, 23. Now, you can do this another way. You can do this as 2 independent choices. How? Well, you can think of the way that I'm going to do the first 3, which are numbers, and the way that I'm going to do the last 3, which are alpha characters. Think about this. This right here is a permutation. No repeats. We exhaust our set of data. We could say this is 10p3 because I have 10 objects and I'm choosing 3 and I can't replace them. That is going to give us 10 times 9 times 8. The second part is 26 objects, you're choosing 4. So I can also think of this in that way. Most people kind of, I think, tend to do this version because it just makes sense logically, but I want you to see that you can also do that. Okay, let's try a combinations question. So let's do a combination problem. I'll start it off pretty easy and then we'll bump it up a notch. So let's say that we are choosing, again, we could be choosing a committee to plan maybe homecoming. Okay. And maybe there are, 30 people to choose from that have signed up that they want to be on the committee, but we're only going to pick 5. So how many different committees could be created? That's the question, right? Okay. So we know that this is a combination because it's a committee, which means it doesn't matter who I pick first versus second versus third. It just matters that they make it on the committee. So order doesn't matter. Okay. So I have 30 items and I'm putting them together 5 at a time. Okay. So I could do that longhand, which is 30 factorial over 30 minus 5 factorial, 5 factorial. This would cancel out after 25, so 30, 29, 28, 27, 26, and then I'd still have the 5 factorial. This is if you wanted to do it by hand. You certainly do not have to. You could simplify it. Your calculator will do it just fine. So let's do that. I'm going to do it. So I'm going to put in, for me, I have to put the 30 first. Then I hit math. I'm going to make sure I choose combination. And I'm going to say combine them 5 at a time. So there I go, 142,506. Okay, not too shabby. Okay, let's say that you were planning homecoming. We'll do a separate one. Let's say you're planning homecoming and you want to pick your committee to have both juniors and seniors, right? Maybe you have 30 juniors to choose from, but you're only going to pick 2. And you have 50 seniors who said they signed up and you're going to pick 3. That way you have, a good spread, but you have more seniors than juniors. Okay. So in this situation, if we're trying to figure out how many different committees that we can make, first of all, it's still a committee, which means order doesn't matter, which means I'm still doing combinations. But I have 2 different sets of data, guys. So you got to think of this as an independent selection. You have the ways that you can get the juniors And then you're going to multiply that by the ways that you can get, the number of ways you can get the seniors. Once you think of it like that, this is actually not that bad. How many ways can you get the juniors? Well, you have 30 of them, and you're going to combine them 2 at a time. It's a combination because order that you pick doesn't matter. The seniors, you have 50 to choose from, and you're going to pick them 3 at a time. And then I'm going to multiply those two independent things because picking the junior doesn't affect picking the senior. And then I'm going to multiply those two together. So let's see what we get. Again, I can go back to my calculator, and I'm just going to type this in. So I'm going to use this one, but I'll make it a 2. Enter. Times, I'm going to use my parentheses. Then I have 50. 3 at a time. Okay, so it looks like I got, and actually I'm going to do this so we can see them separately. So it looks like for juniors, I had 435, and for seniors, I had 19,600. So let me fill that in, 435. Oops. So I had 435 times 19,600. And then when I multiplied those two together, that's when I got the 800. Look at that. Look how quickly that went up. 8,526,000. Woo. Different ways. Isn't that crazy? I mean, that just seems like that gets so large so quickly. But again, that's because I have such a large pool and I'm only taking a few at a time. And combining different juniors with different seniors makes that a difference. Okay. So there's your permutations and combinations, your independent choices, your selections. Some of the homework is literally going to be as easy as just doing like 30C5. And some of them are going to get more difficult. As you can see, they can absolutely get more difficult, and they will. And I anticipate us talking in class about these problems because they are going to be a little challenging. So good luck with this. This is the second part. Again, we have one more video that we'll do this coming weekend on the binomial expansion, which uses combinations. So we'll talk about that then. Otherwise, happy counting.